And so let's review the equations that we got to last time. We had kind of talked about some special cases. We had the internal energy and irreversible expansion against a constant volume and isothermal reversible expansion. And then we had this really important relationship between the heat capacity at constant pressure and the heat capacity at constant volume. Now we're going to reach back in that first part of the course, and all of those times we calculated the heat capacity, the CV, we'll add one more R to it. So if I say helium, what's the CV? All you have is translation. So it's going to be 3/2 R. And then what's CP? You add one more R on there. So 5/2 R. You just add another 2 halves. And so you'll see these in some of the calculations that we do. And remember, we're using that mental activity that we were doing with the degrees of freedom from the first part of the course. So I just want to make sure I emphasize that we're pulling that piece forward on CV and using it for these problems. If it's going to be a gas in our engine that's nitrogen and oxygen, those are diatomic molecules. And so then they're going to have 5/2 R for their CV, 7/2 R for CP. So you just add up those degrees of freedom, not using the vibrations, just using the translations and rotations. Okay. And so let's do an example cycle problem. So this would be the type of problem you set up. 10 moles of helium is taken through this particular cycle. Calculate the heat, the work, delta U, delta H for each segment. And then we'll add them all up. We'll do the whole cycle. But we do this in parts. We go from point 1 to point 2, point 2 to 3, and then 3 back to 1. And so you have those different legs. And so for vocabulary word, those are legs of a cycle, those different transformations. And then we're going to calculate those state variables for each point on that PV graph. So most of these are going to be plotted pressure versus volume. So temperature is coming out at you, and you really can't see that. Okay. Number of moles of gas is going to be constant for these cycles. Doesn't have to be, but that, again, is going to be one of those assumptions that we'll make, that if there's exchange with the outside environment, like we have for automobile engines, we also have intake. And so we have output for exhaust, we also have intake. And so we'll say within the cycle it's the same number of moles. It just happens to be different molecules, but it's the same number of moles going through our cycle. So a lot of times we can say it's the same number of moles going around. We have to solve for pressure, temperature, volume, and look at those relationships. So some of the things that we notice in doing a problem like this, the very first thing you do is look for any kind of special cases in this situation. So we look to see if any of these apply. Isothermal processes, because if it's isothermal, it means it's the same temperature, and the things that depend upon temperature are internal energy and enthalpy. And so the internal energy would be 0, the enthalpy would 0, because they depend upon a change in temperature. So if it's isothermal, you know immediately there's no change in internal energy, no change in enthalpy. We will figure out next time what an adiabatic process is. But if you have an adiabatic process, it's going to be an expansion or a contraction, but it will not be isothermal. The temperature will change. But the temperature will change, but there won't be any heat flow. So the change in internal energy will be the work that's done. And then if you have any constant volume processes, you have 0 expansion work. So you're not expanding or contracting, so there's no expansion work. So you know that W is 0 for that case. And that delta U would be equal to the heat change in the system. So these are should be committed to memory. These should be back of your head type things. When you see an isotherm, you know that leg has a delta U of 0 and a delta H of 0. If you see an adiabat, which will be labeled or by familiarity, if you've worked these cycle problems, you should say, okay, these are the 2 adiabatic legs. I know Q is 0 for both of those legs. Anything that you want clarified on this before we move on? So these, again, star this page. Those are sort of a mental framework when you approach these problems to recognize these things. If you don't recognize these things, you will just be lost, and you won't know why you're lost. So then we go through the cycle problem, we evaluate any of the simplifications that we can. So we look at leg 1 to 2, and we see that that's expansion against a constant pressure. Now, can you see that in this chart? I don't want to go to the next one until everybody can see that leg 1 to 2 is a constant pressure process. You see it's a horizontal line. You draw it over to the pressure, it's the same pressure for point 1 as there is for point 2. Okay, so that's a constant pressure. Now, how is it expansion? You know it's expansion, but for two reasons. One, look at this little arrow. That arrow is telling you the direction that the process is going. And so because it's going to the right and volume is also increasing to the right, you know it's going to a larger volume. So that's expansion against a constant pressure. And this would be the equation for work. So whenever you find you've got this expansion against a constant pressure, your memory should say, oh yeah, I've got an equation for that. So at least I know how to calculate the work. And so you can write out, you know, on the side or whatever your equations. You say, okay, leg 1 to 2, I know the equation for work for that leg. And then going from 2 to 3, that's an isochore. That may be a new term for you. This up here is an isobar. And this is an isotherm. So iso meaning same. So same pressure, same temperature on this bottom curve. This is the same volume. And you can see that on the volume axis. So volume of 3 and volume of 2 are the same. Now if there's no change in volume, then work is 0. And so then any change in delta U is going to be equal to Q. And then we have an isotherm, which means delta T is equal to 0. So delta U and delta H are 0. And Q equals the minus work. So equal magnitude, opposite sign. Anything to be clarified here? Okay, so then I guess that was the first thing, is to kind of see if anything is recognizable, the different processes in the legs, and kind of get familiar with what's happening along the whole cycle. Now we actually get down to the specifics. Let's calculate the state variables for every point in the cycle. And so this is called the state variables table. It's not really called that in any of the books that I've read. This is my tool that I talk about because it's just a systematic way to approach these problems. So build a table where you have P, V, T, and N, the number of moles. That should be a lowercase n. Autocorrect made it a capital N. So the number of moles, the temperature, the volume, and the pressure. And we use the ideal gas law. And we're going to just find a way to enter this table with the things we know. So to me, this is like the best problem. I hate Sudoku, but I love this. It's pretty much the same thing, okay? You got to find a way to get into the table, right? You got to find out, all right, I know if I've got this square and that square, I can figure that square. And so you just have this great little problem called a state variables table, and you fill out all the empty squares. Now, you fill in what you know right away. So we know the pressure was 10 atmospheres, and it was given 1 liter. So we know for point number 1, we had 10 atmospheres and 1 liter. Okay, and then this is the same pressure over here at point 2, so that's 10 atmospheres and 20 liters. It said in the problem that 10 moles of helium was taken through the cycle. So we have 10 moles of helium for all 3 points along the way. And then we have also the volume of 2 and 3 are the same, and so we have 20 liters here and 20 liters here. So you see we've got quite a few squares open, but we've got some missing. And we're using the ideal gas law, so we just have to find one column that's just missing one cell. And we've got one variable, we've got one unknown, and one equation. So you just work it until you fill out the whole table. So we can't really do number 3 because we've got 2 variables there and only one equation. We've got the PV equals nRT, and we've got 2 unknowns. So we're going to have to hold point number 3 aside for a while and do 1 or 2. So I've got 1, So since we know pressure, volume, and number of moles, we could solve for the temperature. It's P1 V1 over NR. It's a really cold temperature. It's probably not a realistic cycle, but it's a good problem. But 12.2 Kelvin, I don't know exactly how we would get that cold side to consistently be 12 Kelvin. But that's what we have here for this problem. And so that's so we've got point number 1 set, and point number 1 is an isotherm with point number 3. Now we could go and just write 12.2 Kelvin over on point number 3 because it's on the isotherm. It's the same temperature. That's one of the things that I think people get stuck on. They don't recognize whenever there's an isotherm that connects the two temperatures. And so 1 and 3 have the same temperature. Once you solve for 1, now you know the temperature of 3. Yeah. And then we have 3 out of the 4 variables on number 2, so we can calculate that one. The temperature at point number 2 is 243.7 Kelvin. Pretty hot. Okay. How did we expand against that constant pressure? We raised the temperature like crazy. So we pumped in a lot of heat, and we pushed that piston or whatever this thing is expanding against up to 244 Kelvin. So we put in a lot of heat on leg 1 to 2. Okay. And then we got rid of that heat to drop the pressure down. So at that 20 liters, we sucked a lot of heat out to drop the temperature back down to 12.2 Kelvin. And so then once we have over in point 3, we have 3 out of the 4 variables, we can solve for the pressure. So it goes from 10 atmospheres down to half an atmosphere. And now we have the whole state variables table filled out. So you can see how that it's very systematic. Are we going to need every number in this table? Maybe not, but it doesn't matter. That we need to have it totally filled out so that when we calculate the change in energy, we need delta T's. Okay. When we're doing, say, an isothermal expansion or compression, we need both volumes. Okay, and we need that temperature. So we need to be able to pull the variables out of this table, so it's good to just fill out the whole thing. Now, that may not be possible. Maybe you'll have to make some assumptions. And this is where you write out your assumptions. I'm assuming 1 atmosphere at this point in the table, or I'm assuming room temperature here. So there may be some things that you have to do to fill out the state variables table and making assumptions. And that's always uncomfortable because you're saying, well, gee, what am I doing here? I'm guessing. Well, you just got to tell who you're communicating with that that's what you're assuming. So now let's calculate for each segment all of the different parameters that we have. Work and heat, delta U, delta H. And so for the work, it's minus PX delta V. So the external pressure we calculated was, in our state variables table, was 10 atmospheres from 1 to 2. And then the change in volume, the final volume was 20 liters. The initial volume was 1 liter. And so we can put those numbers in there. Minus 10 atmospheres times 20 liters minus 1 liter. This is a thing that many people also screw up. They put the delta V as 10 liters, but it's not. 20 liters, but it's not. It's 19. So a lot of people will mistake that. They'll say, oh, it went from 1 to 20, so that's a difference of 20, and it's not. They just did a bad math in their head, and they should have really taken the difference. So this is about being very meticulous. And so it's 19 liters times 10 atmospheres, and then we want to get out of liter atmospheres and into joules. And so we use that conversion of 101.325 joules per atmosphere. And then it ends up being in the thousands, and so we go ahead and convert it to kilojoules. So it's negative 19.3 kilojoules. Whenever calculating work, stop and do a sign check. Does the negative sign make sense?
Because there's work.
The system is the gas.
Work coming out of the system.
Yes, it pushed the piston back. It did work, so it should be a negative number. The system lost the capacity to do work because it did work. It did work, and now it has less capacity to do work. 19.3 kilojoules left the system by pushing that piston back. So the sign makes sense. If the sign didn't make sense, you might have switched your volumes, or you might have forgotten the initial negative sign right here. Okay? So that's why I let you have a note card. But make sure your note card's right. Sometimes people will say, I missed that one. That's so easy. We look at the note card and it doesn't have the minus sign on it. And then, it's a bad thing. So that's the work done from 1 to 2. What's the delta H? Well, we take CP times delta T. And remember, delta T is T final minus T initial, not just big minus small. So we have the number of moles, 10 moles. 5 halves are, this is helium, and that looks like we're taking rotation into account, right? But we're not. It's 3 halves are for translation only, and then we add an extra 2 halves because it's CP. Delta H goes with CP. Delta U goes with CV. Delta H goes with CP. So go ahead and write that down just to get it in your head. Delta H goes with CP and delta U goes with CV. So this is the CP, the heat capacity at constant pressure for helium, a monatomic gas. If it was argon, it'd be the same. Then 244 minus 12. So final minus initial. So we have positive 48.2. That should make sense too, because we had, in order to raise that temperature and drive that expansion, we had to put in a lot of heat, and delta H is the heat of reaction. So it's measuring how much heat was put into the system. The internal energy change uses CV, same equation, but just with a different heat capacity. And so we end up with a slightly smaller number, 28.9 kilojoules. So the energy of the system did increase when we moved the temperature. So it did work, but yet the energy still increased. So, and then finally we have the delta U is Q plus W. So Q is delta U minus W, and W is negative. And so the heat from 1 to 2 is equal to the enthalpy. So that's all 4 of the main, properties for leg 1 to 2. Pause for anybody that wants clarification. It's not difficult, but you need to have all of your equations in hand and be able to do them. Okay. So now let's go from 2 to 3. This is an isocore or constant volume cooling. It's easy to calculate the work because delta V is 0, so work is 0. So we have the same equation, minus P external delta V. You could also, if you did use the isothermal expansion or compression, it would be V final over V initial, and they're equal to each other, so you have the natural log of 1, which is 0. Okay, so either one of those equations would give 0 work. If volume doesn't change, you have 0 work. Delta U using CV. Remember T final minus T initial. So now you have 12 Kelvin minus 244. And that's what gives you the negative sign. So we have sucked out 28 kilojoules of energy of the system by cooling it down. And then using CP for enthalpy, T final minus T initial, we end up with negative 48.2 kilojoules. So we pulled that much heat out of our system. And then in terms of enthalpy, and then the heat loss is delta U minus W, and so we end up with negative 28.9 kilojoules because the work is 0. Okay. Any questions on this one? Yes.
So for delta U in this one, we're using CV this time, and then
Now the rows were kind of switched. Hopefully that didn't confuse you. On the previous slide, we calculated enthalpy first, and so it was CP on top, and then the next page was CU. It was delta U on top. I mean, it just the way I did it.
okay, gotcha.
Yeah.
That's what threw me off.
Okay. Yeah. Sorry. Good question though. And now let's do that last leg, 3 to 1. And so going from point 3 to point 1 is isothermal, so we don't have any change in internal energy or enthalpy, because those rely on delta T, and delta T is 0. If delta U is 0, then the heat is equal in magnitude but opposite sign from the work, and we can calculate the work because this is reversible isothermal expansion, or compression actually. It's compression because of the arrow. You notice we're going to a smaller volume. And so this will be V final on top, which is volume 1, and V initial on bottom, which is volume 3. 10 moles, the gas constant R, which would be the 8.314 joules per mole Kelvin. 12 Kelvin is the temperature because it's an isotherm. We don't have any delta T because it's isothermal. So it's at 12 Kelvin, and 1 liter over 20 liters. And so it's a positive number because 1 over 20 is less than 1, and the natural log of something that's less than 1 is negative. And so that kills that negative sign in front and gives us a positive amount of work. Now, does that make sense? Anytime you calculate work, do a sign check. It's positive work because we're doing compression. We're putting work into the system. We're compressing it. Now it has, after that compression, a higher capacity to do work. And then Q is equal in magnitude but opposite sign of work, so it's minus 3 kilojoules. So this is how you do a cycle problem. You find any assumptions to help you pick your equations, and you start on the state variables table. You find a beachhead in that table, right? Just like a Sudoku puzzle. You find the easy ones to fill out, and then you start filling out the more complicated ones. And you do the columns that only have one missing variable using the ideal gas law, and then you start working on the other columns. You might have to make some assumptions. If you end up to the point where you have two unknowns and you still only just have one equation and you can't get there, either something is equal to something else in the table and you haven't identified that, or you're at the point where you need to make an assumption. We'll do another example here in a second. So let's go around the whole cycle. So the delta U for the whole cycle is the change in internal energy from 1 to 2, 2 to 3, 3 to 1. And so we had 28.9 kilojoules going across from 1 to 2. We had negative 28 going down to 3, and then 0 change to get back up the hill. So delta U, when you go all the way around and add up all 3 cycle legs, is 0. Okay. And then H, you go around all 3 legs, you had 48.2 kilojoules, a negative 48.2, and then 0. And so that equals 0. And that's another example of what we're talking about, a state function.
Yeah.
So it didn't matter that we went around this whole cycle. We're back to where we started in terms of internal energy and internal enthalpy. But work and heat are path dependent. We go around this path, and now we've done work. We've gone around this path, and now we've taken in heat. So let's add those up. The work going from 1 to 2 was negative 19.3, so it did work on the surroundings. It didn't do any work going from 2 to 3, and then to reset the system at such a cold temperature, it was really easy to compress that gas. And so we compressed it at 12.2 Kelvin, and that only took 3 kilojoules to compress it at that temperature. So that's how we trade on the differences in terms of how hard it is to compress a gas. We get the system to do work at high temperature, and then when we work back on the system, we do that at low temperature. So we reset the system in terms of its volume at low temperature, and we heat it up or somehow introduce energy, and then it does the work at high temperature. So it puts out a lot more work than we put in. Okay, we have to add in heat for this to work. For us to get the system up to a high point where it can do a large amount of work, we have to add heat. So that's our cost in heat cycles, is the heat that we put in. So the efficiency is the amount of work done by the cycle. And it might do work on multiple legs. And so you add up the net amount of work done, and then you divide by the heat that you had to put in. So the amount of heat you put in, essentially, you paid for. You burned something, you constructed something. That's why I love solar energy, because you're not actually paying for the fusion reaction that's happening on the sun. You may be paying for the optics in order to concentrate it, but you're not actually paying for that source of heat. Whereas, if we're, burning natural gas or whatever, we had to, extract that, and we paid money for that. So that's our cost. That heat in is our cost. How much work out did we get? And so we got 16.3 kilojoules of work out of this cycle, but we had to pay for 48.2. Notice that it's not the net heat. Okay, it's the amount of heat in. The net heat was 16.3, and the net work was 16.3. And so if you're using the net heat, you'll always get an efficiency of 100%. But you didn't get all the money back when you took the 28 and the 3 kilojoules out of the system. That's just lost. That's just lost heat. And if you could turn that into another use, you could up your efficiency. But a lot of times, that's just the cost of doing business. You put in the heat at 48 kilojoules, you paid for that, and then it's really difficult to capture the 28 and the 3 that leave. Okay. So it's how much heat you put in, and it's the work that you've got out of it, and that's the ratio that calculates the efficiency. And so it's 0.34 efficient, and that's pretty good, actually. It sounds bad, but like a gasoline engine's 25% efficient. Diesel can get to 30 to 35. Okay, so diesel engine, especially when you put a turbocharger on there, where you're stuffing air in there and getting complete combustion, it's doing more work when you stuff in more air, and so then you're able to get it to 35%. Our electrical grid, burning natural gas or coal or any of those things, is only about 31% efficient. So really going from a really efficient high-pressure fuel rail diesel engine to an electric car that's just plug-in, you're going from a 35% use of the original fuel down to 31% efficiency use of the original fuel. And we'll get into that in the last fifth of the course or fourth of the course when we talk about energy sources and sinks. We'll look not just at specific processes that their efficiencies, but the global use of energy and the efficiency from chemical fuel all the way to the electrical outlet. So if that sparks your interest, there's more to come on that. Now let's talk about the Carnot Cycle. That's the next big cycle we're going to do two more. But the Carnot Cycle is the most efficient cycle that we can come up with. It uses all reversible legs. Some of these legs, these straight across isobars and isocores are not reversible. But these smoothly varying curves are isotherms and adiabats. And the Carnot Cycle is a combination of 2 adiabatic expansions and 2 isothermal expansions and compressions. Now, it's the most efficient. And if we were to run a Carnot Cycle with such a dramatic change in temperature, there's a temperature equation. The Carnot efficiency just depends upon the hot and cold reservoirs. So this is the equation for the efficiency of the Carnot Cycle. And we had a dramatic difference in our temperature. We had 12 Kelvin versus 244. So if we were to run this same temperature difference as a Carnot Cycle, it would be 95% efficient. It would be very difficult to do, like I said, to hold that cold reservoir at 12 Kelvin after we're dumping in 19 kilojoules or 48 kilojoules of heat. It'd be hard to sink that heat and not have the cold reservoir rise a little bit in temperature. Okay. But it would be an improvement on what we have. So, the cycle efficiency that we have, that would be 45.8 kilojoules of work instead of 16.3 if this was a Carnot Cycle. So I just took that efficiency for the Carnot Cycle and multiplied it by the amount of heat that we put in. In our process, we put in 48 kilojoules of heat, and if we got 95% of that out as work, we would have gotten 45 kilojoules of work instead of 16.3. So what's the improvement? It's at 45. The Carnot would have delivered 45.8, And our cycle delivered only 16.3, so it would have been 2.8 times more efficient. So we would have gone 2.8 times further. We would have done, whatever work we were getting out of it, we would have gotten almost 3 times as much work out if it was the same temperature setup, but with a Carnot cycle.
Isn't this like the ideal, but it's not achievable?
Yeah, it's very close, but yeah, it's not achievable. But yet, it's such a simple, like, best case scenario. You just look at the 2 temperature reservoirs, and you know what you could get out of this. So it's the upper limit, I guess. We would not be able to get more than, with these 2 temperature reservoirs and our current setup for heat, we would not be able to get more than 45.8 kilojoules of work out of it. So it tells you what the upper limit is. And this is useful when you talk about, well, they've got cars that could get 500 miles per gallon. No. There's no arrangement with those temperatures that's going to give you that much work on that much energy. So the amount of gas you put into it, a gallon of gas, gives you so many joules. And so, but it would tell you the upper limit. I don't know what that upper limit is, but it's not 500 miles. Might be 150. Might be something way better than what we have now. But it's useful. This Carnot Cycle system is useful because it will tell you the max amount of work you can get out of a system. We all ponder on that for a second while I set up the Stirling engine. So I brought an engine to class. I was so excited about this. You can thank Thomas if you ever meet him. He got into, he just ranges around looking at engineering sites and math sites and stuff. And he asked me, what do you know about Stirling engines? And I said, nothing. And so he did his homework. So this is a Stirling engine. You can see that. I'm going to turn on the video and get it over here. So, okay. Okay, maybe down here. That's pretty good. And so it's got 2 pistons here, and it's got those pistons are connected to a little flywheel, and then as that spins, it's got a little electrical generator on it. Okay. So it's got a heat source here, which is an alcohol lamp, and it's got a little LED that sits on the generator. Hopefully I got that set up the right way. Yeah, you can see that. Should have my goggles on.
Don't tell Dr. B.
Yeah. It's non-toxic, it's ethanol. Toxin is the dose, right? And what's interesting about this is it's called an external combustion engine. Okay, so it's heating up that cylinder from the outside. So it's combustion, but it's external to the cylinder. It's got 2 little graphite pistons in there that seal it pretty well. And I'm just heating up that one side, the hot side. So it's just going through the cycle. It's just going through its expansion and compression cycle. And what's happening is this hot gas is expanding. It's connected to this cold side over here. And the gas is compressing over here, which is pulling that piston in, which resets the hot side. And so heat's flowing from the hot side to the cold side, and it's driving that compression and expansion. And then the LEDs, they just put a little controller in there to make it blink. and do crazy stuff. So that's the Stirling engine. It's not a very, there's some problems with it, I would say, in terms of how it works. But, you know, the nice thing about it is you could burn a really nasty heat source. You could, you know, things that you couldn't put inside a cylinder, like an automobile that would be really corrosive and so on, you could burn those in a Stirling engine, and you're not going to corrode the inside of the cylinder. You're not going to mess with the piston head or anything like that. You could burn leads, you know, and get mechanical energy out of it. It's not very, I mean, look how easy it is to, you know, slow down. So, but that's just because it's a tiny little engine. Now what I want to do is I want to blow out the flame and measure the temperature of the hot side. That doesn't seem right. Yeah. The first one I got was like 56, but I guarantee that's not 56. That feels about like 170. Yeah. I think I need to change the batteries on my thermometer. But so that's the Stirling engine. So let's go back to so this is the cycle for the Stirling engine here. So here we have a PV plot, and we have A and B, and we have some constant volumes. The way those pistons work, when one reaches its maximum, or I should say it's pushed all the way in the cylinder, that's V minimum, but then the other one is connected on the flywheel 90 degrees to that. So as that one comes away, the other one is also coming up. And so there's a constant volume leg, and then they both rock back. And so that's an overall expansion, and then there's a constant volume leg on this end, and then they all rock forward. And so there's two constant volume sections, and then there's two isothermal expansions. Isotherms being the hot side and the cold side. And so we can set up this PV plot for the Stirling engine, and then we can go through the state variables table. And this is an example where we don't know. I mean, you just buy this from physicstoy.com or wherever we got it. All right, they don't tell you the parameters of this because they just think it's a toy. But I'm looking at that going, what's the volume of A and the volume of C and all these things. I want to fill out the state variables table. So I got out my ruler and I started measuring, you know, what the stroke length is in millimeters, and you know, what's the diameter of the piston and all of that. So I went through all of these measurements. The diameter of both pistons is the same. It's 12 millimeters. You don't really need to write all this down. It'll be in the notes. And so then the areas, I calculated the areas. So 226 square millimeters. And then the stroke length is we'll calculate the displacement. It's 13 millimeter stroke length. So that's the distance between the back side and the front side of the flywheel connection. So as it pushes the piston in and out, I can calculate now the volume that it displaces with that piston. We've got the area times the distance of the piston movement. So that's the volume that's being pushed or pulled by the expansion and the compression. Okay. And so that's the displacement. So the difference between VC, where all the pistons are forward, and VA, when the pistons are back, or vice versa on that one, is going to be the displacement. And so it's calculated at 2,941 cubic millimeters, or 0.002941 liters. And then the minimum volume, VA, there's a little spherical half sphere tip on the hot side. I'm assuming the inside of the cold side has the same little spherical tip. I can't see that. It might be flat. Okay, but assuming it has the same shape on the inside of the cold side as it has on the outside of the hot side, then I calculated the minimum volume of VA. Now going from cubic millimeters to liters, looks tortured, but you'll never make a mistake this way. And that is just doing this conversion from millimeters to centimeters cubed. Because it's a cubed unit, milli is 10 to the minus 3, and centi is 10 to the minus 2, and they're both cubed. Well, 10 to the minus 2 and 10 to the minus 3, that's 10 on the bottom cubed, so 1,000 millimeters cubed per centimeter cubed. You may have that memorized, but this is a way to do it where you won't screw up. Okay, and I'm always trying to teach you the tools of how to do it without making a mathematical error. And then you've got 1,000 cubic centimeters per liter. So this conversion will convert that 905 cubic millimeters to liters. So that's the volume of the tip of that cylinder. Adding in that half of that stroke length would be VA, would be the minimum, and then adding in the volume of the tip, we get VA's volume here, and then VC plus that difference is going to be the volume of VC. So here's our state variables table, and we have our two volumes. What else do we know? We're going to have to make some assumptions. We've got a huge table, and we've got one equation, and we've got 1, 2, 3, 4. Well, let's just pick B. We've got 4 unknowns. Right. So we're going to need to make some assumptions. Now, this is not airtight. It's close, but it's not airtight. And so I would say that when it's operating at I would just pick C, volume C, and pressure C to be 1 atmosphere. Okay, so I assumed that the temperature at point C, so that isotherm was room temperature, and that the pressure at point C was 1 atmosphere. So that allows me to get a beachhead, but is that supported? I don't know. Could I put a voltmeter on there and measure the current that it could deliver and so on? Yes, and that would give me the amount of work it's doing electrically. Then I would put in the efficiency of the electric generator, and I could calculate how much work I'm getting out of this engine. If that doesn't match, then my assumptions are wrong. Okay. So then that would help me make better assumptions. But at this point, I haven't done those measurements, and so we can go with this assumption. So then that allows me to calculate the number of moles. And the number of moles in this system, it's happening so quickly, there's really not a lot of exchange of gas with the outside. And so I'm just going to say that the number of moles inside those pistons don't change. It's just like a spring that's converting heat flow into mechanical motion. And so the number of moles of gas in there are just being compressed and expanded, but they're not really changing. And so I'm going to say that the moles are constant all the way across. Again, is that an assumption? It may be. I think that one's actually more defensible than my room temperature and 1 atmosphere. And so now we've got TC here. It's going to be the same for TD. And so now I've got all three. I've got 3 out of the 4 on the far right, and I can calculate some of those pressures. So I've got an assumption for TA. I have to make that assumption. I don't know what the temperature is for that. I tried to measure it. This thermometer measures about an inch diameter, and that's about a ½ inch. So I wasn't able to get a good reading on my bulb. I'll have to redo this with a thermocouple. So I'll blow out the flame and stick a thermocouple on that glass, and it'll be more accurate than my finger. And so once I measure that temperature at point A, then we can fill out the rest of the state variables table. And so we'll do that next time. We'll go ahead and fill out the state variables table for our Stirling engine, and then we'll calculate the heat and work and everything for all the different legs and see how much heat's being captured from that flame, that ethanol flame, and converted into work. And I think it'll be a blast. Okay. Now I'm going to post these notes today, and also I'm going to post a nice little article on the Stirling engine so that you can read a little bit more about it. Okay. Glad you were here.